And this was this issue of should you maintain boundaries of geographic boundaries. And then the issue was, one of the other things they were looking at is do people of sort of common beliefs, et cetera, should we put them together? And so this is one of the things that the district is dealing with. And so anyway, it is, I forget who it says here it is. Samuel Lair. Did anybody know Samuel Lair? Anyway, he's a PhD student here at the college in politics. And so anyway, he's got a petition, and he says, in my opinion, Senate District 29 fails two of the Commission's criteria representing communities of interest and coordination of county lines. It's also interesting that there's an article in yesterday's Hillsdale Daily News about the Democrats and gerrymandering and the Democrats concerned that there's gerrymandering going on to affect the Republicans' control. And we noted that earlier that the large majority of states are controlled by a single party. And of course, that's in many of the states. That is also who's drawing up the district boundaries for the House and the Senate, in the legislature, and in the U.S. Congress. So anyway, if you come across, who did I say this was? Samuel. So if you come across Samuel Lair, you might just say, hey, we've been talking about you in public choice. You're famous. All right. Any questions on what we were going about last time? We were looking at the tit for tat strategy and how the and again, there's no theoretical proof about that would be the optimal strategy in a game where it was played over a whole number of times. But it turns out that it turns out to collect the most points in Axelrod's tournaments, and again, we've noted why that might happen. We said because it's a clear strategy that it rewards cooperative behavior and it punishes uncooperative behavior, and it is forgiving, so that if you decide you're going to start cooperating again, then your opponent's going to start cooperating again. And then we noted that if you misperceive that what someone else has done, you think that they cheated but they really cooperated, then if you're doing what they did last time, what you perceived them doing last time, you can get this back and forth where you get one party cheating on one time and then the other party cheats the next time. And so the only way to get back into equilibrium would be to have a second misperception. So one of the things that you might do to sort of fight this misperception is to say, okay, I'll punish if you cheat, let's say, twice, right, or a few times. So that you say, okay, there's some chance that I misperceived what was going on, so I'm not going to respond right away. I'm going to wait, and if you do, if you cheat twice in a row, then I'm gonna cheat. Okay, and again, you will get less points if they actually do cheat, right? Because you're gonna go ahead and you're not gonna punish them the next time if they actually do cheat. But it does, in a sense, it's sort of like this issue about transactions costs and making a decision, right? The optimal majority, right? Maybe unanimity isn't right, the perfect way to do it because there's transactions costs. Similarly here, there's some possibility of a misperception cost. And so what you might do is, rather than doing exactly tit for tat, say, okay, I think they cheated, but I'm not 100% sure they cheated. And so what I'll do is I'll just go ahead and cooperate this next time. If they cheat again, then okay, I'm gonna respond that way. So again, as we noted, why do you have government institutions that are out there to deal with this this steal, not steal, prisoner's dilemma. And so again, why are we discussing market failures, and we talked about externalities and government goods? Okay, when if you have a Pareto optimal state of the world in a competitive equilibrium, one of the things you answered on the midterm, well, when do you need government, right? When it goofs up, okay? If the price is equal to marginal revenue, or excuse me, if marginal revenue is equal to marginal cost to set a price, then you're going to not have the equilibrium condition, or the condition that you need for efficiency. So similarly here, why do you have one reason to have courts and that sort of thing is that government is there to enforce cooperative behavior. So if you have situations where you have prisoner's dilemma sort of situation, stealing, enforcement of contracts, those sort of thing, then you'd have a reason to have a role for government. That's a reason that we might form government. All right. The last piece of game theory we're going to do is in Chapter 7, and this is the idea of a mixed strategy. So what we've been talking about so far is a pure strategy, okay? You either throw the fastball, or you anticipate the fastball, or you throw the curve or anticipate the curve. So you have a pure strategy. Now, what we're going to look about here is a mixed strategy. And what we're looking at is a simultaneous game, okay? So right, not a sequential game, a simultaneous game. So you've got this payoff matrix. And what we're going to be talking about here is a zero-sum game. Okay? So we have a zero-sum game. What I win, you lose. What you win, I lose. And so now the question is, when we looked at the very beginning in the intro part, one of the things was to mix your plays, right? We talked about, do you always want to run the ball or whatever? And so what we're going to look at here is when you might mix your plays and how might you optimally mix your plays. So what we're going to take a look at is basically you want an unpredictable behavior, right? I don't know that you're always going to throw the fastball, or I don't know that you're always going to pass, or I don't know that you're always going to give the ball to number 6 to run, okay? So you want to make some unpredictability to that. And an unpredictable strategy can be better in some instances than playing a pure strategy, okay? So we're going to look at this can be better than a pure strategy. So rather than throw the fastball, throw the curve, okay, there's going to be some probability I'm going to throw the fastball and some probability I'm going to throw the curve. So let me just give you a little example of this. Suppose that we have the following payoff matrix, and we have the pitcher up here, and the pitcher is going to throw, and the pitcher could throw a fastball, or a pitcher could throw the curve. And we're going to have the hitter over here who can anticipate the fastball or curve. And suppose we have, again, this is going to be the percentage of times that they get a hit, right? So the batter's trying to maximize that, and the pitcher's trying to minimize that. So suppose we have 60 and 10 as the payoffs, and 20 and 30. And what are we going to assume? We're going to assume that the assumption here is the other player does the best for them, given what the other player is doing. So if we take a look at this, we're saying, okay, given that the hitter is going to anticipate the fastball, what's the best play for the pitcher? The pitcher ought to throw the curve. Given that the hitter is going to anticipate the curve, what's the best thing for the pitcher to do is throw the fastball, okay? So in this particular case, we know that the pure strategy is going to be for the pitcher. The pure strategy is going to be what? The pure strategy is going to throw the curve. And if the pitcher is going to throw the curve, what's the hitter going to do? The hitter is going to anticipate the curve. And what's the solution to the game? The payoff is going to be 30. So 30% of the time, the hitter's going to get a hit. Notice that I didn't set it up so that there was a dominant strategy, right? If we had a dominant strategy, we'd know what was going to happen. But I didn't set it up so there's a dominant strategy. So we know what the solution to the game is if it's a pure strategy. I'm just either going to throw the curve or I'm going to throw the fastball. So now what we're going to do is we're going to say, let's see if we can figure out how should I mix my plays. How should, if I'm the pitcher, we'll start out with the pitcher's perspective, how should I mix my plays so that sometimes I throw the curve or sometimes I throw the fastball? And let's say we're going to actually, with this diagram here, or this payoff matrix, going to turn out that pitcher's going to throw the fastball a third of the time. But it's not going to be, okay, I throw the fastball, then I throw two curves, and then I throw the fastball, and then I throw the two curves, right? Because you'll know what's happening. So the deal is, what's the probability I'm going to throw the fastball? So if the answer comes out a third, then what we're saying is, at any one time that the pitcher's throwing the ball, there's a 1/3 probability they're going to throw the fastball, and a 2/3 probability they're going to throw the curve. Okay, so don't confuse that. Okay, we're going to end up showing that they're going to throw the fastball a third of the time. It doesn't mean that it's predictable how they're going to do it. Right? It's got to be any one particular throw. I'm the hitter. I know there's now, if again our answer is going to be a third. I know that there's a 1/3 probability they're going to be throwing the fastball. So let's see how you do this. Well, the first thing that you do is you're going to convert this payoff matrix into a diagram. And the way the diagram is going to look like this, it's going to be, we'll put 0 and 100%, and we're going to look for x, and that's the percentage that the pitcher is going to throw the fastball. So we're looking at this from the pitcher's perspective. Okay. Now, when x equals 1, okay, that is when this is the fastball and this is the curve. Okay. When the pitcher's at the fastball, I got to have, if the hitter's at the fastball, they're going to get 60. And if the hitter anticipates the curve, they're going to get 20. So I'm going to put 60 up here, and I'm going to put 20 there. Okay? So when I'm converting this table into this payoff matrix into a diagram here, I'm going to have it when the pitcher throws the fastball. I've got 60 if the hitter's at the fastball and 20. And then if the pitcher's at the curve, I'm going to have 10 and 30. Okay? So I'm going to have 10 here, and I'm going to have 30 there. And so this is the payoff when the hitter's at the fastball. Okay? So if you actually just sort of mathematically, when I have the two extremes, if you draw a straight line between those two extremes, it gives you what the payoff's going to be as you move along this axis, which is the x. Okay? Just turns out that that's the way it sort of mathematically that's the way it works. So if this is then what do we have over here? We have the hitter's anticipating the curve. Now, what are you trying to do? If you're the pitcher, you're trying to minimize the maximum, right? You're trying to have the least percentage of time that that they're going to get a hit. So if you minimize the maximum, what did we assume? We assume that the hitter's going to do the best thing that they can given what the pitcher's going to do. So from here to here, the best thing for the hitter to do is to anticipate the curveball. Okay? So if the pitcher throws the curveball all the time, if the percentage of the times they throw the fastball is 0, right, then the hitter ought to be anticipating the curveball. And as you move along here, the hitter's got a higher probability, and you're assuming the hitter knows what's going on. They've taken 415, and they know what's going on. Then what's going to happen is they're going to be along here, and then at that point they're going to switch over, and a hitter's going to do the fastball. So this is going to end up being the payoff, and this is going to be the amount of time. This is going to be the percentage or the probability that the hitter's going to the pitcher's going to throw the fastball. Okay, so we're looking at the pitcher's perspective. So how can we figure this thing out? Well, we can write an equation. There's two equations, right? And what I'm looking for is where these things are equal to one another. If I know the equation for this line and I know the equation for that line, then I'll figure out when they're equal to one another, and that'll be what the solution is. So the question next becomes, how do I get the equation? So let's take a look at this in terms of how to get the equation. So what we're looking for x, right? So we're looking for the percentage of times that the pitcher's throwing the fastball, or the probability the pitcher's going to throw the fastball any one time. So if I'll move this down a little bit. If what we're looking for, the hitter fastball equation, so what do I need? I got x times something plus 1 minus x times something. Okay? Because x is the percentage that they're throwing the fastball. So it turns out this is the equation for the hitter throwing the fastball. It's going to be x times some number plus 1 minus x times some number. And it's got to come out to be what it looks like along here. So when x equals 1, then what's going to happen? The hitter of the fastball is going to turn out to be 60. That is, when the pitcher throws the fastball all the time, what's the value of x? What's the value of the equation? The value of the equation is 60. Okay? If x is 0, then what ought to happen? The value of the equation's got to be 10. Okay? So when I'm looking at this, I'm going to look at when x equals 1, I got to plug in what is going to give me the number 60. So if x is 1, it's going to be 1 times 60 plus what? 1 minus 1 is 0, right? And when it's 0, then the answer is 10, right? So when x is 0, I got to have the answer being 10 here. So the equation for the hitter throwing the fastball is got to be x times 60 plus 1 minus x times 10. Okay? So again, I have the notes, and you can take a look at the notes. But you ought to be able to, again, make sure that you are understanding how you convert the table to the picture to the equation. Okay? So the equation is always going to be x times something plus 1 minus x times something. And I know what that value's got to be when x equals 1. And I know what the value's got to be when x equals 0. It's 0 times 60 plus 1 is equal to, times 10 is equal to 10. Now, if we do this thing's got to be equal to the hitter anticipating the curveball. Okay? And what's that going to be? That, again, is going to be x times something plus 1 minus x times something. But on the curveball sign, what do we need to have? If on the curveball side, I've got to have it so that the x is going to be, if the x is 1, then I got to have 20 over here, right? When x equals 1, the hitter on the curve's got to be 20, and then it's got to be when x is 0, then it's going to be 1 times this thing when x is 0, and that's got to be 30. And so that gets us the equation on the hitter on the curveball side. Okay? So now what do you got to do? I'm looking for the intersection. So I'm looking where the two lines intersect. These things got to be set equal to one another. And if you just go through your, I don't know, 9th grade, you can solve for x, right? If you solve for x, it'll turn out that your answer is going to get 1/3. You're going to get x equals 1/3. If you solve for x, on both sides, you can go ahead and do it yourself, sort of play around a little bit so you're understanding what's going on. You're going to end up with x going to be equal to 1/3. Now, again, that's the probability that x is going to be, it's the probability that pitcher's going to throw the fastball. So if you're the hitter and you know what the payoff matrix is, then what you're going to know but you can calculate that the pitcher's going to, 1/3 probability that they're going to be throwing a fastball. And then we know what the payoff is, right? Because this is equal to this, so I can stick the 1/3 in there, and what I'm going to get is, if I put x equals 1/3, you're going to end up with 26.677 as what your answer is. Okay? So, what do you do? Yes. That's the payoff. So, if what I do is, right, if I look at what the payoff's going to be, the value of the payoff is going, at this point, the value of the payoff is going to be 26 2/3. That's what it is. It's 26 2/3. Okay? Yes?
I'm not really sure who's payoff in the matrix. Is it payoff to player 1 or player 2?
It's going to be what the payoff is to whatever we've got in here, right? Because this is going to be the percentage of the time that there's going to be a hit. Okay? So it was 30, right? So the percentage of times that they're going to get the hit, that's what we're really looking for. What's the percentage times they're going to get a hit? So it's the same on, this is the percentage times they're going to get a hit when the pitcher throws the curve.
Yeah, but what I'm confused is that, it's not clear whose payoff is that, because, it seems to me like this way, there must be indifference between, two options. Is that, the two equal each other?
Remember, this is a zero-sum game. So all we're saying is that if this thing turns out to be 1/3, right, which is what we're going along here. If this is the percentage times that we're throwing the fastball, if that's a third, then what's going to be the percentage of times that they get a hit? When this is 0, if the hitter is going to be on the curveball, notice that it doesn't matter whether the hitter's anticipating the curveball or the fastball, right? Because they're equal at that point, right? So it's going to be the return to the hitter from anticipating the curveball or the hitter anticipating the fastball because they're equal to one another there. Okay? Does that make sense? Okay? So again, because these two lines are equal to one another, this is going to be the payoff. The 26 2/3 is going to be the payoff. Okay? So now what we maybe want to take a look at is what happens if we get to the hitter's point of view. Okay? So this is the pitcher's point of view. We could have done it from the hitter's point of view. If we do it from the hitter's point of view, now what we're going to do is we're going to look at what is the percentage that the hitter anticipates the fastball. And again, that's going to go from 0 to 1. And so we're looking for X. What's the percentage? What's the optimal percentage for the hitter to anticipate the fastball, right? So again, we're going to do exactly the same thing, right? We're going to say, okay, if when we're looking at the hitter anticipating the fastball, then what I need is I got to have 60 and 10, right, as the two points there. So when the hitter's anticipating the fastball, I got to come up with 60 and 10. So I'm going to have 60 over here, and I'm going to have 10 over there, right? And of course, this is when the pitcher's looking at the throwing the fastball. And if we look at the other end of it, if we look at the pitcher when the pitcher throws the curve, when the hitter anticipates the curve, when the hitter's anticipating the curve, I got to get 20 and 30. Okay, so what you do is you look at that table. You got the 4 points, which are the end points of the two things. And so here I'm going to have, what is this? This is where the hitter doing the fastball. And when the hitter anticipates the fastball, it's the pitcher. When the pitcher's throwing the fastball and the hitter is anticipating the fastball, that's my 60, right? And when the hitter's anticipating the curveball and when the hitter's anticipating the curveball, so we're down here to a 0, and the pitcher is throwing the fastball, then what are you going to get? You're going to get 20. And so I've got the pitcher throwing the fastball. I'm going to get 60-20, right? So I'm getting these two terms. And similarly, when I do the pitcher with a curveball, I'm going to have those two. Okay? Well, you can do the same thing. And take a look at this. I'm going to have, if I'm looking, what am I looking for the two things to come together? If we play around with that, in fact, what I'm going to do is let you guys maybe do it on your own. But just to give you the answer here, I'm going to end up with the pitcher at the fastball and the pitcher at the curve. We're going to end up with x times 60 plus 1 minus x times 20. And that's going to be equal to x times 10 plus 1 minus x times 30. Okay? And if you solve for x is going to turn out to be 1/6. So what does that tell you? It tells you that if you're looking at it from the hitter's perspective, the hitter's going to anticipate the fastball 1/6 of the time. So the probability that the hitter is going to anticipate the fastball is going to be 1/6. All right? So figure out what the equation is. To figure out the equation, it's always going to be x times something plus 1 minus x times something, where x is the percentage that you're talking about throwing the fastball. Or you could have done it with the curve, and what would you end up with? You end up with the 2/3, right, instead of 1/3. Or if you'd done the curveball, the hitter anticipating the curveball instead of the fastball, guess what? You'd have come out with 5/6 instead of 1/6. So again, I can get the payoff by just plugging in what the x is into either of these diagrams. And what are you going to come out with, you think? You're going to come out with 26 and 2/3 is what you're going to come out with. Okay? So what is the hitter trying to do? The hitter's it's knowing that the pitcher's going to do what's best for them. The hitter's trying to make it as big as possible, right? The hitter is trying to what? Maximize the minimum. So the pitcher is minimizing the maximum, and the hitter is maximizing the minimum. It's a zero-sum game, right? So one party is always trying to minimize the maximum, and the other tries to maximize the minimum, depending on what you put in here, right? And so it's which party that you put in the positive for. So you got a zero-sum game. I can figure out what the solution is for either party, and it's going to turn out that you're going to get the same payoff whether you're minimizing the maximum or maximizing the minimum. Okay, and we'll come to that in a moment. Now, it turns out that there's a shorter way to do this, and if you actually plug in, first of all, there's a footnote in the book where it shows you that, algebraically you can show that this is going to turn out. But algebraically what you do is if you want to have a shortcut to solving the equation, it turns out that what you do is you look at the difference between these two, okay? So you look at the difference between the fastball and the curve, and that's 50, okay? So what you're doing is you're looking at the difference between the fastball and the curve, and the difference here is 10. And what's going to happen is you're going to have I'm going to go this way, so that if we're looking at it from here, that the hitter ought to be doing this. The ratio's got to be 5-to-1. So to get the ratio 5-to-1, you can make it so that it's 50/60, right? And if you do this, it's 10/60. And so what does that tell you? It tells you that the hitter ought to, again, you take the difference here to get the ratio, just take the total, 5-to-1 is 50/60ths and 10/60ths, and you move them this direction. So that what's going to happen is 1/6 of the time fastball, 5/6 of the time curve, right? Which is what you get if you actually go through and do all the, do the calculations by setting up the equation, okay? Now, if you want to do it the other way, that is, what's the pitcher going to do? You do the same thing. That is, the difference here is 40, and the difference here is 20. So it's got to be 2-to-1. And so if what you do is you do 40/60 and 20/60, and you move them this way, what do you get? You get 1/3 fastball, 2/3 curve. So, a shortcut to doing, writing out the equations and solving them, you can just look at the payoff matrix. And so if you're looking at a two-person zero-sum game, then what you're going to do is figure out what the difference is on the fastball, what the difference is for the curve. You're looking at the hitter, make the ratio the other way so that the fastball is going to be the 10/60ths, the curve is going to be 50/60 or 5/6, and you get the same answer that we did if you were to just solve out what the equation is. Okay? Now, yes. Because it's 5-to-1. So if I were, I can get 5/6 by doing, 5-to-1. So that I just took the two of these and added them together to get the 60, because it's 60. 5-to-1 is the way to get the 5-to-1 is to say 50/60ths, right? And then 10/60ths gives me that 5-to-1 and 1-to-6, okay? So I got 5/6 over here, 1/6 over here, and that gives you the 5-to-1 that you have in that table, right? So this table, 50/10 is 5-to-1, okay? So that's just a mechanism to get you to the 1/6. And same thing down here. What I did was I took the 40 and the 20 and added them up to get the 60 to put it in the denominator. And that gives me the 2/3 or 40/60ths and the 1/3, which is the 20/60ths. Yeah, 1/3 fastball, 2/3 curve, and that's what we had when we solved out the equations. Okay? And again, if you want to demonstrate why this shortcut works, there's a footnote in the book that goes through and just shows you algebraically why that shortcut would work. It's the same thing as solving the equations. Got that, Alex? Is it okay? All right. All right. Now, it turns out that the payoff is the same when it's the maximum. I just mentioned it's the maximum of the minimum or the minimum of the maximum, right? So the payoff is the same. If I do it from the hitter's perspective or whether I do it from the pitcher's perspective, the payoff is going to turn out to be the same. When the pitcher's doing the optimal thing for them, given what the hitter's doing, and the hitter's doing what the optimal thing for them, given what the pitcher's doing, then the payoff is the same. When you minimize the maximum, that's what the pitcher was trying to do, right? Was to minimize the maximum. Or if you maximize the minimum, right? This was what in our example, this was the pitcher and this was what the hitter's doing. It turns out that they're equal to one another. And again, if you just plug in for the equation that we just, that I erased here, but the equation that we did for the hitter, and you plug in the hitter's optimum, and you calculate the payoff, what are you going to get? You're going to get exactly the same thing. You're going to get 26 2/3. Okay? So if I can either solve it for the pitch, if I want to know what's the payoff, then all I need to do is solve for one of them. I don't have to solve for both of them. And why is that? Well, it's pretty complicated. Solution. There is just sort of, if we're looking at the Public Choice Hall of Fame, von Neumann and Morgenstern, they proved that they proved that this was that every zero sum two-person game. Okay, so I've got a zero-sum two-person game with two strategies. Okay, so we don't have 20 strategies, there's two strategies. It turns out that there's going to be an optimal strategy, and this condition holds here. There's an optimal strategy, which is a mixed strategy, right? So there's an optimal strategy, and the max of the min equals the minimum of the max. So if I just want to know what the payoff is, I don't have to solve it for both of them, right? I don't have to look. I can either look at it from the hitter's perspective, or I can look at it from the pitcher's perspective, and I'm going to get what the payoff's going to be. All right. So again, start out with a payoff matrix, turn it into the picture to the diagram over there. You got the 2 points when they're and you pick. X is going to be the probability or the percentage that you're going to do the one thing rather than the other. Then what you do is that you find the two endpoints. Either the pitcher's throwing the fastball, it's going to be whatever it is when when it's 1, when X equals 1, it's going to be whatever the payoff is for the hitter doing the fastball and hitter anticipating the curve. Then go back, put it where the curveball is the other option. That's when X equals 0. Make the 2 points there for picking it off of the payoff matrix, draw the lines to connect them, and then X times something plus 1 minus X times something is going to be equal to X times something plus 1 minus X times something. You know what to put in for the X when it's 1 minus, if it's 1 minus something, I got X, when X is 1, I'm going to have whatever's in that, the end point, okay? And when X is 0, then I got what's in the other end point, and I do it for both equations and set them equal to one another, and you can solve for X, okay? Or once you've got, you could just shortcut the whole thing if all you want to know is, what's the optimal strategies, then you can just do the table and do the shortcut part without having to solve the equations. To get the payoff, you'll have to know what one of the equations is to get the payoff. And again, since they're equal to one another, you only have to do it for one of them to get what the payoff is. Okay? So just sort of like you did on the Pareto optimality thing, right? Okay, here's what the condition is. Here's what we assumed, and then what happens is if they cost minimize or if they utility maximize, then this happens, and then assuming everybody's the same as a price taker, then this, margin rates of substitution equal to one another, or margin rate of technical substitution equal to another. Okay, so just go through that. You know how to do the mechanics of producing that. Okay, we got the general idea on that? Okay, again, the notes, and there's different examples in the textbook, and this is in chapter 7, so there's different examples in chapter 7. And I think I may have I think I even have examples of this as well in your folder in the game theory part. I have some examples of mixed strategies where I calculated it out for you. All right. So what if you have a dominant strategy? Okay. Let's say if you have a dominant strategy, then let's think about what's going to happen here. Give you an example. If I had 50, 20, 30, and 25, and I had the pitcher up here, and I had fastball, curve, fastball, curve. Now what I've done is I've set it up so there's dominant strategy, right? That if the hitter anticipates the fastball, the pitcher ought to throw the curve. If the hitter anticipates the curve, then I ought to throw the curve anyway, right? So I've got this dominant strategy. If what you did was you converted that into the picture, if we convert that into the picture, then what are you going to get? You're going to get 30 and 10, or excuse me, 30 and 50, and you're going to get 25, and you're going to get 20. And okay, so if I pick the mixed strategy, and let's say this is the hitter with a fastball, and this is the hitter with the curve, notice that the intersection is going to end up with a payoff which is here. But that's less than if, that's higher than if you had a pure strategy, right? If what we're doing is we're assuming that the hitter's going to, you're trying to minimize what the hitter's going to do. And so what's going to happen is, what's the payoff going to be? The payoff is going to be where that intersection is. And that payoff is less than what it would be if you chose your dominant strategy, which was the curveball. So that's just to show you a picture that you're going back to the same story here. You're going to look for a dominant strategy, right? So if you don't have a dominant strategy, then the mixed strategy is what you're going to end up with. If you have a dominant strategy, then you'll end up with picking the dominant strategy, okay? All right, so for next time, we got one more little thing to do on this. We're going to look at what happens if you improve your game. And if you sort of think about it, if I were just to improve one aspect of my game, it's, I got something like, this, and I'm going to end up there. And then if I make this one better, the intersection is going to go that way, okay? So it's just what we talked about before. If you get better at the run, then what's going to happen is that they're going to now start moving towards the run, and the opposing person is going to move towards more towards the run than they did. All right. So next thing we're going to do then is we're going to do the alternative different ways of voting. So we're going to move into the voting alternatives. So go ahead and take a look at the textbook in that section, and take a look at the syllabus, and that's where we're headed, is the next part.